Hello, bonjour, grüß Gott, labadiena. Welcome to the 9th week of Statistical Mechanics, Algorithms and Computations from the Physics Department of École normale, supérieure. During our course, we have mostly concentrated on equilibrium statistical mechanics. Our algorithms allowed us to compute partition functions, energies, and condensate fractions. But they were rarely concerned with time-dependent phenomena. Physical time played a minor role, except in the molecular dynamics calculations for the hard disks. The Monte Carlo time really was of secondary importance. For example, the Wolf cluster algorithm that we discussed last week had a dynamics that had nothing in common with the physical dynamics of the Ising model. In this lecture, we explore time-dependent phenomena. And strangely enough, we are right back with the local Monte Carlo algorithm, as it provides often an excellent model for the time evolution in physical systems. So, what we are looking for is an efficient implementation of Markov-Ising.pi. In Dynamical Monte Carlo, we are stuck with a given dynamical rule. And we want to implement this rule as efficiently as possible. In this lecture, we will treat Markov-Ising.pi and study a faster than the clock implementation and also its main limitation that is called the futility. In this week's tutorial, we plunge into a great and very general method called simulated annealing. Simulated annealing is a tool for solving difficult optimization problems with or without a relation with physics. It consists in reformulating the optimization problem in terms of an artificial physical system whose ground state at zero temperature or at infinite pressure contains the solution to the original task. This state is then approached through a slow decrease in temperature or a slow increase in pressure. We will apply simulated annealing to the famous 13 sphere problem that already Isaac Newton worked on. Simulated annealing gives a great solution. In this week's homework session, the final homework session of this course, we will also be concerned with simulated annealing in the 13 sphere problem and the equally famous traveling salesman problem. So, let's get started with week 9 of Statistical Mechanics, Algorithms and Computations. To begin with, let us consider a magnetic field as shown here and a single Ising spin whose dynamics we want to study. We set the temperature equals to 1 and the energy of this spin is equal to minus h if it is up and is equal to plus h if it is down. In short, the energy of sigma is minus h times sigma, where sigma can be plus or minus 1. To simulate the dynamics, we use the Metropolis algorithm. Minimum of 1 pi nu divided by pi old. So the probability to flip the spin from minus to plus is equal to 1. because the statistical weight of the new configuration is larger than the statistical weight of the old configuration. And the probability to flip from +1 to -1 is equal to minimum of 1 pi nu divided by pi old is exponential of minus beta h divided by exponential of beta h is exponential of minus 2 beta h. In Python, this gives the following program, naive spin dynamics.py, where we have set beta equals to 1. Now notice that if at time t the spin is down, it will certainly be up at time t plus 1. This is the essence of metropolis dynamics, and we don't discuss here whether this is realistic. In any case, this algorithm satisfies detailed balance, and in the long run, it means at long times, the two configurations up and down will be visited with their corresponding statistical weights. Pi up proportional to exponential of beta h and pi down proportional to exponential of minus beta h. So now let's look at the movie version of naive spin dynamics.py. Here is output of this program at high temperature. There are a lot of flips. And here is output at lower temperature. You see, for a long time nothing is happening. The spin is in the up position. Then there is a flip, immediately followed by a backflip. And then followed by a long desert of the spin being up. And here is the dynamics of our system at very low temperature. Nothing going on, and just an occasional flip, and our computer heating up without any result. Now remember, the probability to flip from down to up is equal to 1. And the probability from up to down is equal to exponential of minus 2h. So now, to make progress, we choose a particular value of h. In fact, we choose logarithm of 6 over 2. So now, the probability to flip from up to down is exponential of minus 2 logarithm of 6 over 2 is equal to the exponential of minus logarithm of 6 is equal to 1/6. So look at this flip die. It has 5 neutral faces and one face that says flip. So simulating the metropolis algorithm at magnetic field 1/2 logarithm of 6 is like rolling this die. So let's roll it. First trial, no result. The spin does not flip. Second trial, third time, we are getting quite tired. No result. Fifth attempt. Sixth, no. 7. So now we have to flip the spin. In Python, this gives the following program, naivethrow.py. And here is output of this program. So now let us program this problem a little more intelligently than we have done before. So the probability of throwing a blank face of our beautiful flip die is equal to 5/6. The probability of throwing twice a blank face is equal to 5/6 square. And the probability of throwing k times a blank face followed by once the flip face is given by 5/6 to the power of k times 1/6, or 1 minus 5/6. So this is equal to 5/6 to the power of k minus 5/6 to the power of k plus 1. So this can be made into a tower sampling problem between 0 and 1 with horizontal lines at 5/6, 5/6 squared, 5/6 cubed, and so on. We throw a pebble into this tower, and if it falls, for example, in the upper box, we have a new flip right away. If it falls into the second box, we have to wait once. If it falls into the third box, we have to wait twice. To find out the number of times we have to wait, we have to compute the box, which means 5/6 to the power k plus 1 is smaller than the random number, is smaller than 5/6 to the k. Taking logarithms, we find that k is the integer part of the logarithm of the random number divided by the logarithm of 5/6. And this means in our naive throw program that the time after which we have a new flip is given by 1 plus the integer part of the logarithm of the random number divided by the logarithm of 5/6. So in Python, this gives the program fastthrow.py. Its output is indistinguishable from the naive program, but it advances one iteration per accepted flip and not per time. It is for this reason that it is called a faster than the clock algorithm. Of course, a very simple one. We may now write the fast spin dynamics program as shown here. It will remain exactly one step in the downspin configuration with spin equals to -1 and an average of 6 steps in the upspin configuration, so that the magnetization on average will be 6 minus 1 divided by 7, 5/7. You can obtain the same result also by a pedestrian approach. So now, before continuing, please take a moment to download, run, and modify the programs we just discussed. So we had the die throwing programs, naive throw.py, and the fast throw.py that implemented the faster than the clock idea. The output of the two programs is completely indistinguishable. And then we had the related programs, naive spindynamics.py and fast spindynamics.py, that implemented the dynamics of a single spin in the magnetic field. From a single spin in a field, we now pass on to a full-fledged simulation of the Ising model on n sides in the faster than the clock framework. We consider a spin sigma, all the spins, that depends on time. And we denote by sigma k the configuration that comes out of sigma by flipping the spin number k. the energy change that is associated with this spin flip is delta E equals to the energy of sigma k minus the energy of sigma. In the metropolis algorithm, the probability to go from sigma to sigma k is given by 1 over n minimum of 1 exponential minus delta E. The 1 over n stands for the probability of sampling the spin number k. In the Ising model and its variants, for example spin glasses, at low temperature, most of the spin flips are rejected. So, let's roll back our sleeves and implement the faster than the clock approach for the Ising model. Let's avoid all rejections. But there is a problem. In the dice rolling algorithm fastDie.pi, we notice that the quantity that was important was not 1/6 the probability to have a flip, but it was rather 5/6 the probability of doing nothing. Now, in our n-side Ising model, we also have to compute the probability of doing nothing. But as we have n choices for doing something, computing this probability takes a bit of time. So we can compute now lambda, the probability of doing nothing, that was 5/6 before, is given by 1 minus the sum of all the probabilities we just wrote down a few seconds ago. And we can implement the faster than the clock approach through the tower sampling from lambda, lambda square, lambda cube, and so on. In Python, this is implemented in this program, dynamicEasing.py. And you see that there are two tower samplings. The first tower sampling is in lambda. It is from 0 to 1. And it computes after which time we accept a new spin flip. Then we have to decide which spin to flip. And this again is discrete probability, and it is done in a second tower sampling from lambda to 1. And it is there that we compute k, the new value of the spin that is going to flip. Output of dynamicEasing.py is completely indistinguishable from the Markov-Ising.py. And the only problem that we have is that doing one iteration of this algorithm takes of the order of n operations. Besides that, there is no rejection in dynamicEasing.py. The complete recalculation of lambda, the probability of doing nothing, can be avoided because flipping a spin somewhere in the system does not change the local environment elsewhere. So the number of environments of a spin in respect to its neighbors falls into a finite number of classes. The number of upspins and downspins that are neighbors of a given spin. And flipping a spin somewhere in the system just changes the numbers of members of each class. This was first implemented by Bortz, Kalos, and Leibowitz in 1975. They called their algorithm the n-fold way, where n stands for the number of classes. Let's take as an example the Ising model in 2 dimensions with periodic boundary conditions. As you see here, the number of classes are 10. From an upspin with 4 neighboring downspin to a downspin with 4 neighboring upspins. The tower of n probabilities can thus be reduced to a tower of 10 classes of spin flips if only we know the number of spins per class. So in this example, the central spin that we want to flip has just 1 plus neighbor, so it is in class 3. Flipping it brings it into class 8 and makes us change also the classes of the neighboring spins. This very elementary bookkeeping is written up in dynamic easing patch.py. With respect to the original version, dynamic easing.py, where each spin flip involved of the order of n operations, now we can do one spin flip even for a large system in of the order of 1 operations. At small temperature, this algorithm, dynamic easing patch.py, is much faster than the original Markov easing.py. But remember that it implements exactly the same dynamics, moving from accepted spin flip to the next accepted spin flip. So, before continuing, please take a moment to download, run and modify the 2 programs we discussed in this section. For once, there was dynamic easing.py that worked with a tower of n probabilities, and the nice n-fold way algorithm first implemented by Kallos, Bortz and Lebowitz in 1975 that uses the n-fold way and goes from the tower of n probabilities to a tower of 10 probabilities. So the complexity of this algorithm is O of 1 per accepted spin flip. So in conclusion, we have given in this lecture an introduction to faster than the clock algorithms that implement efficiently the dynamics of our system. These algorithms expend work per accepted move and no longer per attempted move. But going from the work per attempted to the work per accepted move involves bookkeeping. This bookkeeping makes also that in many applications they are not as good as they seem to be, because you may have to go from one configuration A to configuration B. You may have to do some bookkeeping as we showed in the easing model, and then on the next move we will simply go back from B to A. This is called the futility problem. To overcome this futility problem, many people have implemented quite elaborate algorithms that even increase the expense per accepted move. In this week's tutorial, we will take up the study of dynamic algorithms from another point of view, the one of simulated annealing. Simulated annealing is a great optimization algorithm. It also shows that the sampling approach is not only related to integration, as we have said for many weeks now, but it can also be used for searching and for orientation in complicated spaces. So have fun with this week's tutorial and homework session, and see you again next week in the final week of statistical mechanics, algorithms and computation for a discussion of the alpha and the omega of Monte Carlo, followed by a resume and by a big party.